So today probably we're going to have our last class on statistical mechanics if everything goes well. So when I use the word statistical mechanics, there is something special that distinguishes this from something that you've studied in your first semester, which is mechanics. So this is something you've studied in your first semester. This is something that we are going through right now. Could you please raise your hands and tell me if you know what the difference between mechanics and statistical mechanics really is? Based upon the 3 or 4 lectures that we've already had on statistical mechanics, what is different in statistical mechanics?
Statistical mechanics we study things at micro level, statistically, and in mechanics we deal with our daily life.
So you think it's really a difference in scale? Mechanics is something large and macroscopic, and statistical mechanics is something at the microscopic scale. Any other ideas? Yes?
Statistical mechanics is based on probability,
And mechanics is based on certainty. So one good answer which makes somewhat sense is, in statistical mechanics we talk about probabilities, we talk about large numbers, and we find out the probabilities that a particular state exists or doesn't exist. So we deal with large particles, large number of particles. They could be smaller particles, but we deal with generally large number of particles. This observation the student has made is that mechanics deals with macroscopic objects and statistical mechanics with microscopic objects is true and to an extent, but not really true, because atoms can also be dealt as from the perspective of mechanics. For example, an electron is being accelerated in the presence of an electric field. So you just apply Newton's laws of motion. There's a force acting on the electron, charge times the electric field, and it accelerates the electron. So this is mechanics. So Newton's laws can apply to microscopic objects as well. So this is partially correct. This is wholly correct, that statistical mechanics deals with small particles but large numbers of them. So the law of large numbers can apply, and you can talk about probabilities. Whereas mechanics, you're sure of everything. It's deterministic. You know where the particle is going to be if you know its present. You know the present, you know what the future is going to be. If you know the present, you can extrapolate what the past has been. Any other difference between mechanics and statistical mechanics? आप बताएं, आपने हाथ खड़ा किया था पहले. Right. Anything else? Conservation of energy, but energy is always conserved. Quantization.
Like continuous concept energy, or you think discrete.
So the way we've dealt with statistical mechanics is that we've introduced the quantization of energy already, and we've seen how energy can be distributed in those quantized levels. But if there were some other teacher of statistical mechanics, he would not have used the concept of quantization altogether. It's just that I've used the concept of quantization because I would like to make a gel between statistical mechanics and modern physics. So quantization, though it's a useful concept, but it's not necessary to explain statistical mechanics. Alright? So anything else? Anything deeper?
So statistical mechanics probably cannot be proved by experiments, but when mechanics can, because there are always a certain probability associated with it.
No, but you can prove it by you can prove laws of probability by experiments. You have a dice, you throw the dice a large number of times, you have 1/6 probability you get a 1, you have 1/6 probability you get a 2. So statistical, right, but all of quantum mechanics is probabilistic. You can't say it can't be proved by experiments. So experiments prove statistical mechanics. It works. It's not a figment in our mind. It's not just in our imagination that something that pretty and fancy on the blackboard, but it really works. So experiments can prove statistical mechanics, and they do prove statistical mechanics is correct.
In mechanics, we have a certainty of something happening, but in statistical mechanics, we have at least some probability that.
We've already discussed that. We've already discussed this point. Any deeper idea that you find which comes out as a stark difference? Alright, so I can tell you about it. In statistical mechanics, if you notice, we've dealt with the concept of internal energy. Whereas in mechanics, the objects that we were dealing with, they had no internal energy. They just have center of mass motion, mostly. So there is no concept of internal energy. If you have an object, for example, this tissue box, you place it inside the room, it's at a particular temperature. You place it inside an oven, it's going to be at a different temperature. So nothing visibly changes. The center of mass motion is still the same. The tissue box is still at rest. But what is different in the two scenarios is that the internal energies are different. So in statistical mechanics, we've introduced this concept of internal energy. And then we've seen how this energy is distributed inside the quantized levels. So we've talked about energy distribution. Or energy spreading. How does energy spread inside the system? Or some people would like to call it energy dispersal. थोड़ी सी आवाज ऊंची कर दें थोड़ी सी. Alright, before we move on to investigating the relationship between entropy and temperature, a few appetizer questions. The first question is, I have a mass of copper which is 1 kilogram, and this is placed in surroundings which have a temperature capital T. And this object, this system is in equilibrium with its surroundings. Now I have another scenario in which identical surroundings and the mass is now 0.5 kilogram. And the surroundings have the same temperature. It's copper here, copper here. The first question is, would these objects be at the same temperature? Yes. Would they have the same internal energy? No. Because, really? Would they have the same internal energy? No or yes? Why not? Who says no? Why not? The masses are different. All right. We have more space available for the energy to go. There are more atoms, which means more. So this is the concept I would like to highlight. Now these masses are different. You said that their temperatures are identical. Now the temperature is a measure of thermal energy. Now what is thermal energy? Thermal energy is a measure of the disordered part of the internal energy, and it's a measure of the average disordered energy. So internal energy has orderly components and disorderly components, and there are no orderly components here because this object is not moving. There is no orderly motion. There is all disorderly motion of the molecules or the atoms of the copper. So all of the internal energy is thermal energy. Now the average of that measures the temperature. Now the temperatures are the same, so the internal energies have to be the same. So even though the masses are different, the internal energy, the amount of energy inside this solid in joules, internal energy, is the same as the amount of energy inside this solid. Alright, so temperatures are the same, the thermal energies are the same, and the internal energies are indeed the same, even though the masses are different. The size of the objects are different. Alright, so this is a misconception. Don't fall into this pitfall that the energies are different. The next question is, are the entropies different or they are the same? Now the entropies are going to be different, right? Because this much energy E is now being spread out into twice as more atoms, twice as more oscillators inside this solid than this solid. If this has n oscillators, this would have 2n oscillators. So now the spreading of the energy is larger. Energy is more spread out inside this solid because there are more spaces for the energy to go. There are more energy levels for the energy to go because there are sheerly higher number of oscillators. There are more atoms. So the energy is more dispersed here. It's more randomized here. There is a higher number of microstates in this case. So the energy has more places to go. So it's more spread out. It's more distributed. And it's more dispersed. And the entropy is a measure of this energy distribution or spreading or dispersal. So even though these two objects have the same temperature, they have identical internal energies, they have different entropies. The entropy here is twice the entropy here. Yes, if you define some other measure of entropy, such as specific entropy, entropy per unit kilogram, that's going to be the same. Alright? Or entropy per unit volume, specific entropies, that's going to be the same. But the overall entropy of this object is larger. So S of A is larger than S of B. So this is the first example we've considered. Remember, don't fall into the pitfall of saying energy is a measure of disorder. It's not true. You'll be led astray. आप भटक जाएंगे अगर आप ये सोचेंगे कि एनर्जी इज अ मेजर ऑफ डिसऑर्डर. ऐसा नहीं है बिल्कुल भी. ठीक है, तो जो पुरानी टेक्स्ट बुक्स लिखी गई उसमें इसी तरह था. बट यू हैव टू लिव अवे विद द कॉन्सेप्ट दैट एंट्रोपी इज डिसऑर्डर. एंट्रोपी इज द स्प्रेडिंग ऑफ एनर्जी. And the entropy is higher if the energy is higher and more space is available for the energy to go. There is a higher number of oscillators, a higher number of placeholders. So you have a car park, you have a very large multi-story car park, and the entropy of that car park will be higher if there are more cars in it and there's a higher number of spaces available for the cars. So the entropy really depends upon the energy and its dispersal. It's spreading out. Another question that students have been asking me and which I would like to highlight is the following. And that's in light of the second law of thermodynamics. Suppose you have the earth. The earth now is a very large object. And we have this table tennis ball that is bouncing on the surface of the earth. And eventually we observe it comes to rest. Now this earth is a much larger object than the table tennis ball. This would be about 50 grams. This is about 10 raised to power 30 kilograms. It's huge. So this would have much larger energy than the table tennis ball. So if this earth on average has a larger energy, one could expect intuitively that by law of conservation of energy, that this reservoir of energy can transfer some of its energy to the ping ball that is lying static on the floor and the ball starts jumping in the backward direction like this, and the ball starts rising. But this does not happen, even though it's possible by the law of conservation of energy, because the earth, which has a surplus of energy, a large amount of energy, can transfer some of its energy to the ball. It won't hurt the earth if it did so, but that doesn't happen because of the second law of thermodynamics. Could you explain why this doesn't happen? Why does the second law of thermodynamics prevent such a situation? आप बताएं। बिल्कुल जी जी। The entropy of the earth is much higher. Right. So if the ball and the earth were to share energy, because they are in contact, they want to exchange energy, and they would like to move to a situation where the total entropy is maximized. Since the earth has a very large mass, there are more places for the energy to go inside when in the earth than in the ball. So if there is 1 joule of energy, and that has to be shared between the ball and the earth, there are more microstates available in the earth, because the number of atoms is huge as compared to the number of atoms in the ball. So the multiplicity of the energy, or the number of microstates, or the number of ways in which energy can exist in the earth is very large. Energy is spread out in the earth. So if energy is to be shared, this will have almost zero energy, and this will have all of the energy, because this is a much massive object, right? So that is why this ball would like to remain at rest with zero energy, more or less, and all the energy would like to go inside the earth because of the multiplicity of states, the large number of atoms, the higher number of microstates that are available. Likewise, if I have a cylinder, and inside the cylinder there is a partition, a screen, such that there are some gaseous atoms. We have a monoatomic gas like helium or neon, argon, comprising of single atoms. And all the gas is trapped in this compartment, in the compartment A, and there are no gaseous atoms in B. Now this gas will have a certain temperature, T. Now you slowly lift this partition, you slowly lift it. What would happen? What would happen to the gaseous atoms? They would diffuse. They would diffuse out of compartment A and go into B, right? So I slowly withdraw this screen, it goes up, I take it out. Eventually the same number of atoms would be found in the combined A plus B system. I have to subtract a few atoms from here, right? So in a state of equilibrium, if you allow for this diffusion process to take long enough, there will be an almost equal distribution of gas atoms inside these two chambers. Now the temperature remains the same, which means the internal energy is really the same, right? But now this energy is spread out in a larger spatial area. It's spread out in a larger space. So more space is available for the same energy to be dispersed. The entropy has gone up. And this is why diffusion occurs. The entropy goes up because of second law of thermodynamics. Second law of thermodynamics tells us that these gaseous atoms should spread out in all the space that is available to them. So this process of expansion of a gas or diffusion can also be explained in terms of the increase of entropy. Now the energy remains constant, but more space is available for the energy to be spread out. G.
So why does the temperature remain same?
We keep it the same. We keep it the same. We withdraw the screen very slowly, so it's an isothermal process. And if we do it slowly enough, the temperature will remain the same. The pressure is going to drop, the volume is going to double, but the temperature remains the same. So we can have a process in which we can force the temperature to remain constant, or the pressure remains constant, or neither of the two. Alright, so we know that expansion is a result of the second law of thermodynamics, the maximization principle of entropy. And entropy, remember, depends upon the energy and it depends upon the dispersal. Both of these factors contribute to entropy. और इसी तरह अगर मैं एक और एग्जांपल बनाऊं, if I have the same compartment, A and B, and there is a gas in A and then there is a gas in B, a different gas, and both of them are ideal gases. And if I slowly lift the screen up, there would be an equal distribution of gaseous atoms inside the two chambers. So they will intermix freely. B will expand into A and A will expand into B. So the final configuration will look something like this. Subtract a few atoms from here. Subtract a few atoms from here. This screen has gone up. So this process of mixing, whenever two gases mix, whenever two liquids mix, the total energy remains constant, but now more space is available for either of the gas molecules. For A gas, there is more space available. For B gas, there is more space available. So this process of mixing also maximizes the entropy. So diffusion occurs, mixing occurs, because there is a higher multiplicity available for the same energy to be distributed. The entropy goes up. In other words, it's the second law of thermodynamics, which is based upon the principle of driving the process to a higher entropy, which results in expansion or mixing. And if you look carefully enough, mixing is just the expansion of two gases. There's really no difference between mixing and expansion. So another point that you've already seen, but I would like to emphasize again, is the following. Suppose I have an object that is very large and it's hot. And I have an object that is very far away, but it's a smaller object and it's cold. And the material is the same. I bring this cold object close to the hot object. Now, energy transfer will take place. That energy transfer is denoted by Q. So there is microscopic work or an energy transfer Q from the hot to the cold object. When will this energy transfer cease? When the temperatures are the same, and that is called a condition of thermal equilibrium. But will the energy be equally shared between the hot and the cold object? No, because the masses are different. This hot object has more microstates in it. It has a higher multiplicity or greater room for the energy. So this will have a higher share of the energy. Even though these two objects, both of them are now warm objects. This is warm, this is warm. because they are at the same temperature, a temperature that is intermediate between the hot and the cold object. Both of them are warm, they are at the same temperature, but this has a higher share of the energy. And if these objects are identical, the share of the energy will be proportional to the share of their masses. So energy is distributed, but it is not necessarily equally distributed, rather it is equitably distributed. It's not equal, but equitable. There is equity. Equity समझते हैं? There is equity. Equal नहीं है, equal energy storage नहीं, equity है in proportion to their masses, because you have to consider both the energy and the multiplicity. Now there was a question. I mean, this object will have the same total internal energy than this total internal energy. So there will be no energy transfer. This energy is being shared in a larger volume. More oscillators, more atoms, a higher number of quantized levels. So this energy is dispersed more here. But the energies, of course, are the same in the two warm objects.
There you said the masses are different, but since the temperature are set here, for the energy is also the same. So what if it is here as although the masses are different, but the energy should be the same, because the temperature are the same.
Right, the energies are the same here. Isn't that what I said?
You said that the larger mass would have the greater share.
No, I'm sorry. The two objects, I'm sorry if I made that mistake. The two objects have the same amount of internal energy because the temperatures are the same. This object has the same amount of internal energy than this object. But this has a higher entropy because there are more degrees of freedom available for the energy to go. Right? So this has more energy, a higher amount of internal energy. Right? So I'm sorry for this mistake. Ji.
Sir, you are making the same statement again. You are saying it has higher internal energy. When the temperature
No, it has the same internal energy, but that internal energy has more spaces to go.
So it means entropy is greater, but
Energies are the same. So let me summarize again. In this example, we have two objects. They are at the same temperature. They will have the same internal energy. But this internal energy has more space to go inside this larger object, so it will have a higher entropy than this object. Now there was another question you asked, and that was about equitable. What is meant by equitable?
What is equitable? Entropy is equitable.
Equitable means if I have n atoms here, I have 2n atoms here.
So yet I would, what is the statement regarding what is not equal but equitable? Entropy is not, as in, what does this relate?
So the entropy is equitable. The entropy is equitable. The two objects will have the same internal energy, but that internal energy will be more dispersed here because there are more states available. So this will have a higher entropy than this object. Alright? Alright, now I would like to investigate the concept and the relationship between entropy and temperature. It's a very important and a very subtle concept. So please be attentive. First of all, I would like to tell you that if I have a graph between x and y, and this graph looks like this, then this shape is given a special name. It's called not parabola, or just the shape is called, it's not really a parabola, it's called concave downwards. Concave downwards. Let me just think about one thing. Okay, I stand corrected once again. In this example, this is a hot object, this was a cold object, this is half the mass. This object is brought here, and there is energy transfer between the hot object and the cold object. Now this has a higher multiplicity. This has a higher number of states available. There's more oscillators, there's a higher degree of freedom. Now what's going to happen is that this energy transfer will cease at a point when the two objects come at the same temperature. Now energy has to be shared. Now these oscillators in this object are identical to the oscillators in this object, but there are more oscillators here. So the average internal energy in both of these objects is the same, right, which is a measure of the temperature. The temperature is the same, which means that if you take a certain volume of this object and measure the internal energy in this volume, and you take the same volume in this object and you measure the internal energy, it's going to be the same. But this is a much larger volume, so there will be more total internal energy stored in this warm object, in this larger warm object. Alright? So this will share energy equitably. This will share energy equitably. The energy will not be shared equally. This will have more internal energy. And I am saying this with full confidence. Okay? So this has more internal energy. You're looking at that example? Forget about that example for a minute. This has more internal energy, and the ratios of the internal energies will be the same as the ratio of the number of microstates. Alright? So on average, a volume here will have some internal energy which will be equal to the internal energy in the same volume in this cold object. And that is a measure of temperature, the average internal energy. But overall, this object will have a higher energy stored in it as compared to this object, and we've seen plenty of examples of this kind already. So it's the energy that is stored, shared equitably, not equally but equitably. G. It's the average disordered part of the internal energy, average. Okay? The entropy will be different. The entropy in these two objects is different because there are more microstates here, there is a higher energy here. So the entropy of this object is going to be larger than the entropy of this object.
So the energy and entropy both will be not equal and equitable.
Right, the energy is equitable. If these objects are of the same mass, energy will be shared equally.
The entropy won't.
The entropy will then be the same. अगर ये एनर्जी इक्वली शेयर होगी और ऑब्जेक्ट्स का मास एक होगा, एनर्जी भी दोनों में इक्वल होगी और एंट्रोपी भी दोनों की एक सी होगी. But in this case, the entropies are different and the internal energies are different. Okay, one last question.
They were not the same object.
They were different objects.
Different objects, then would the internal energy per volume or internal energy per mass be same?
If they are at the same temperature, then the internal energy per mass would be the same. Alright, now look at this curve, it's concave downwards. I would like to explore a deeper relationship between entropy and temperature. If I draw another curve between x and y, this kind of curve, this is called convex upwards. I call this convex upwards. Now you have to pay really close attention to these last 40 minutes of the class, because this is something you will not find in this form in any textbook. In fact, all the thermodynamics material that we've compressed in 4 lectures, you will not be able to find in any textbook. So you really have to pay attention. I'm trying to compress a large number of vital concepts into 4 lectures. So you really have to be careful. You will not be able to find all of this material at one place. The first point, if I draw a graph between x and y, which is concave upwards, this is concave upwards, what is the property of this graph? How can you tell whether it is concave upwards or concave downwards or convex upwards? By the slope. So if this is concave, what's going to happen to the slope? आप बताओ स्लोप को क्या हो रहा है, आप पीछे से बताएं जी. हाँ जी जी, स्लोप क्या हो रहा है? डिक्रीज हो रहा है. ठीक, कॉन्फिडेंस से बताएं. सो देयर इज सम स्लोप हियर, and there is some slope here. There is some slope here, and the slope is constantly decreasing, and it's positive. So by looking at the slopes you can tell it's a concave function. ठीक है? Now if I plot on this graph energy, and I represent this by E, which is the internal energy, and here I plot entropy, and this is represented of course by S. Now the graph between entropy and internal energy in most normal objects is concave, and the slope at any point is of course given by ds over de. Everyone agrees with me on that? Now let's suppose that there are two identical objects, A and B, and they are of the same mass, and they are identical, the same material. So the oscillators are the same in both of these objects, and this object is kept at a temperature Ta, this object is kept at a temperature Tb, and this temperature is higher than this object. So this is hot and this is cool. Tb is higher than Ta. So when these objects are far apart, which of these objects will have the higher energy? B. B will have the higher internal energy. It's going to have the higher thermal energy. It's going to have the higher average internal energy. The higher energy, higher temperature. So where will this object be on this graph? Will it be to the right or to the left? It's going to be on the right. And this object is going to be on the left. So I draw a straight line here upwards. This is object B. Object B is somewhere here. This is the entropy of object B. This is the entropy of object B initially. Now object A is cooler, it's at a lower temperature, its internal energy is smaller. So it's going to be somewhere here. A. And this is the entropy of A. This is the entropy of A. This is the entropy of B. Now when B is brought close to A and both of them make thermal contact so that energy can transfer from one object to the other, slowly equilibrium will be established if you wait long enough, if you allow time for the energy transfer. And both of these objects will eventually come to the same temperature. And they will share equal amounts of energy now, because A and B are identical materials and they are of the same mass. Alright? Now what's going to happen on this curve? Now the internal energy of B has to decrease and the internal energy of A has to go up. Could you guess where the final state would lie? Just think about it. I give you half a minute to think about it. Just think about it. They make thermal contact. There is energy transfer going on between them. You wait long enough, equilibrium is to be established. My question is, once equilibrium has been established, where on this curve will this system lie?
Is TA equal to TB, like the difference between them?
What do you mean? TB is higher than TA?
No, it is higher, but in the sense that
So one student has conjectured that it's going to be TA plus T, it's going to be halfway, right? That's your conjecture. It's going to be halfway. It's going to be closer to B. It's going to be closer to B than to A. It's going to be to the right of B. Look, I have to seek answers right now.
This should be the highest entropy, therefore it should be to the right of B.
It has to be to the right of B.
Highest entropy. So it should be point above this one.
It's going to be, which means to the right of B. Any other ideas? So it's good that you learn by counter examples. You learn more by giving wrong answers. Right? So that's the purpose of a quiz. If you give wrong answers, that's alright, because then you know why I was wrong.
Since the total mass increases, will the entity change or the curve change?
The curve is not going to change. So there are three answers that I have found. One is it's going to be in the middle. The second answer, who believes that it's going to be in the middle?
Could you clarify something first? Sir, you said that the internal energy is different once you bring them together, right? We're plotting the graph of entropy versus internal energy. What is this internal energy? Because we're obviously not arguing with the same internal energy at any point, right? Is this the average internal energy? That's the question.
Now it's one object.
Now,
Initially it has this much internal energy, A has this much internal energy, B has this much internal energy. Now what I'm plotting here is what will be the energy of the overall system.
Now we're considering them as one object.
Yes.
But sir, as one object.
Right. Let me seek answers first. That's what I'm going to find out from you. So the first, who are the students who believe that the final equilibrium point is going to be midway? All right. How many students believe that the system will drive to an equilibrium point which is to the right of B? Most of the students think so. But there is one student who's actually given the correct answer. And the correct answer really is that the final state will be in between A and B. It's not going to be in the middle of A and B. Rather, it's going to be closer towards B than to A. And there's a reason behind it. The reason is that there's a slope here. And then there's a slope here. Which of these slopes is larger? This one. This is a smaller slope. What does the slope mean? The slope means if A absorbs energy, how much will its entropy go up? Alright, this is what the slope means. Here this slope is also ds over dE. Here the slope means if object B, which is at a higher temperature, loses energy, because it has to lose energy, it's at a higher temperature, if the energy is to drop, how much does the entropy decrease? But the second law of thermodynamics states that the total entropy must go up. Therefore, if this process is to be driven to equilibrium, the increase in entropy has to be larger than the decrease in entropy in the same system. So if the entropy of A has to go up and the entropy of B has to go down because its energy is going down, then A has to go up more than B has to come down. And that is possible because of the concave shape of this graph. The slope here at the lower, for smaller energies, the slope is higher. So the rate of increase of entropy with energy is higher. And here the rate of decrease of entropy with energy loss is smaller. So what happens is that this system is actually driven to a point somewhere here, which is closer to B than to A. Let me finish. So this is the new equilibrium state.
Which is the average of the tangents?
It's not the average of the tangents. I'll do this very precisely, but first I'm giving a qualitative argument. Let me finish my argument, then I will answer your questions. Here the slope is higher. The slope is higher. So if this object absorbs some energy, which it has to absorb, its entropy goes up much faster. Alright? Now this object is at this point, here the slope is smaller. So if its energy is to go out, which means it has to release energy, then this entropy has to go down, but it does not go down as fast enough. If I plot a triangle here, and I plot a triangle here, for the same amount of energy change, this is delta E. This is delta E. Then it's very obvious that this change in entropy, delta S, is much smaller than this change in entropy. This change in entropy is much smaller than this change in entropy. This decrease in entropy is much smaller than this rise in entropy, because of the concave shape of the entropy graph. So what happens in the process of equilibration is that the system moves towards a point that is closer to B. So this is the equilibrium situation. And the internal energy settles at this point, which is the energy at equilibrium. Alright, so this is made possible because of the concave shape of the entropy graph. ठीक है, now I am ready to answer your questions. जी.
Sir, the total energy has decreased in the system. The total internal energy has decreased.
The total internal energy has decreased.
Because first was E plus B, now it's
First the energy was A plus B. Now the energy is in between.
lesser than total.
Because the temperature has changed. Previously one object was hot, the other object was small. Equilibration has resulted in energy transfer and a new temperature has been achieved. The new internal energy will correspond to the new temperature. नहीं, गायब एनर्जी नहीं हो रही. Okay, more questions, I'll come to that in a minute, because I have to define temperature and then we'll be able to answer that question. Alright?
So when A and B come in contact, so B individually would have a high entropy. And as we know, our system would want a high entropy, so why does B give its energy to A to come to a lower entropy? Isn't that instability of the system itself?
Right. So the question the student has asked is, why does B lose some of its entropy? If B loses some of its entropy, but in its loss there is someone else's gain, so that the overall entropy goes up, then that's a very desirable situation. Because what has to be maximized is the total entropy. It is very possible that the entropy of one particular individual goes down, but the entropy of the community goes higher. Think of it like this way. Entropy is like happiness and energy is like money. So you share money in such a way that the overall community gets happier. So some individual is willing to give away his or her money to another individual so that both of those individuals as a whole become happier. So energy is like money and entropy is like happiness. And what is temperature? I'm going to tell you what temperature really is. More questions. जी. ठीक है, आपको बात समझ आई?
No, sir, but the entropy is smaller here, isn't it? The entropy of the system is smaller than B.
The entropy, the final entropy is this. This is SA plus SB at infinite time, which means once equilibrium has been established. And SA at infinite time plus SB at infinite time is greater than SA at 0 time plus SB at 0 time. The overall entropy has gone up of the combined system. असल में इस सवाल का जवाब देने के लिए I have to plot the graph again, but I have to do it more carefully because this was just for your explanation. I thought that we'll be done with this, but this is the entropy of object A. All right, entropy of object A. with energy. So here we have an entropy scale. I can plot the entropy of object B, right? This is the entropy of object B. Okay? Now there is a combined entropy of A and B, which will be the sum of these graphs. And that entropy will start off from here and it will go like this. SA plus SB, because you have to add SA with SB. So what's going to happen is that you start off with this much energy in A. This is the initial entropy in A, SA at time 0. This is the initial entropy in B. Alright? This is your initial condition. You start off here. Now you don't understand this, that is why I was avoiding this graph. But now let's look at this graph more carefully. Do you understand what I've drawn here? No?
Yes. So we did this in the previous.
We've done this quite a few number of times. Let's. And I'll also answer your question of the total energy. Do you understand the axes? ठीक है, axes की समझ आई? This is the energy in A. This is some entropy axis. Now how does the entropy of A look like? It's a concave function. Okay? So it goes concave upwards with energy. So it increases like this. Okay? Now if object A has energy EA, object B will have energy E minus EA. So when object A has all the energy, this is the maximum value of energy. When object A has all the energy, how much energy will object B have? 0. So the entropy of object B will start from here and it will be concave upwards in this direction. Like this. Okay? So this is a plot of SB versus EA, and this is a plot of SA versus EA. Okay? We've looked at this several number of times. Now initially, when the objects are very far away, most of the energy was in object B because object B was at a higher temperature. So you started off somewhere here. This was your initial condition. ठीक है? ऑब्जेक्ट ए के अंदर कुछ एनर्जी थी, उसकी कुछ एंट्रोपी थी, वो ये थी. ऑब्जेक्ट बी के अंदर बाकी की एनर्जी थी और वो एंट्रोपी हायर है. ठीक है? This is the entropy of object B. This is the entropy of object A. Now what I would like to do, I would like to plot the total entropy, which is the sum of the entropies of A and B. So how would I plot that? I will just take the sum of this graph and this graph. So what is the sum going to look like? What will be the value of the sum here? It's going to be equal to SB. Here it's going to be equal to SA. So the sum will look like this. Now let me finish, please. This is SA plus SB. Alright, this is the total entropy of the system. Now this is the initial condition. This object A, this is the graph for A, this is the graph for B. This object A has a very high slope at this point. Object B has a small slope. This slope is small, this slope is large. which means that if this object absorbs energy, its entropy is going to increase. And it's going to increase much faster than this object will lose its entropy. Because this object is losing energy, its entropy has to go down. But its entropy does not go down fast enough because the slope is smaller. Right? So this object is going to absorb energy. It keeps on absorbing energy till what point? Till the point when the entropy is maximized. Total entropy is maximized. And if you look at this graph, the total entropy is going to be maximized where? Where the two entropies are equal? No. By looking at this graph, can you tell where the entropy will be maximum? Where the slope of this total curve is 0. Which means somewhere here. Here the slope is 0. This is the second law of thermodynamics. Entropy wants to maximize itself. So now this is the total entropy. The total entropy of the system has gone up. Alright? I've answered your question. The total entropy of the system has gone up. And energy is shared between A and B according to the intercept of this graph with the energy axis. And the entropy of the two objects here is not necessarily equal. It's going to be different depending upon the masses of the two objects. If the masses are equal, then the two objects will have the same entropy. Then the maximum will be at this point. So the entropy is maximized, and that is the second law of thermodynamics. Now there are 3 questions. I would like to answer those questions. First from the back. Sorry? If the two objects are identical, the graph will be symmetrical. Sorry, I can't hear you. There, you can consider this graph. This is a more proper graph. No, for identical objects, these entropy graphs will be perfectly symmetrical. For identical objects, this will be perfectly symmetrical. This is the graph for identical objects. This is the total entropy, this is the entropy of A, this is the entropy of B, and equal sharing of energy will take place for identical objects of the same mass. G. I mean, forget about this graph now, because you're having problems understanding this graph. Is this graph clear? Not necessarily. It depends upon what the temperature of A is and what the temperature of B is. If the objects are identical, it's going to be in the middle. The temperature is going to be in the middle. If one object is at 20 degrees centigrade, other is at 30 degrees centigrade, and those objects are totally identical, the temperature is going to be 25 degrees centigrade.
If now when the two bodies are in contact, we are dealing them as the same body. How same body can have two values of entropy?
The question the student has asked is, when the two objects are in contact, we are dealing with one body. You see, we have a system. We have a system comprising two objects. We can talk about the object A alone and the object B alone. What is being maximized is the total entropy of the system. But we can still talk about the object A alone and the object B alone. That doesn't harm us. Alright? Okay, before I answer more questions, you see, I have to finish a few things as well. So I will answer, alright.
So if we start talking about entropy,
Stand up and so that everyone can hear.
if we start talking about the entropy per unit mass and the internal energy per unit mass, so basically we're saying that they will, so a hot and a cold object will continue to exchange energy till the point where the entropy per unit mass and the internal energy per unit mass is basically the same.
Right.
Right? Where neither is favored.
Right.
Is it always the same that the entropy per unit mass and the internal energy per unit mass is always equal whenever they...
If the objects are identical, if the ways in which energy can be spread are identical, if they are the same, objects are identical, the oscillators are identical, then yes. Alright, one thing I would like to ask you now. If you look at these graphs, there is a slope ds over de. Right? And the second law of thermodynamics states that you would like to drive your system such that the overall entropy goes to a maximum, which means that the overall entropy versus energy graph has a slope which is equal to 0. Right? This is the second law of thermodynamics. So this means that d of the total entropy S has to be 0. So I can put an energy in the object A here, right? So this is our condition for equilibrium. This means that d by de A SA plus dSA over dsB over dEA has to be 0, because the total entropy is the sum of the entropies of the objects. So this also means that dSA over dEA has to be equal to minus dSB over dEA. Do you agree with this? In a state of equilibrium. In equilibrium. So intuitively, when equilibrium is established, what is the parameter of the two objects that is equal? The temperatures are equal. We know that. The average internal energy of the two objects has to be equal. That is what thermal equilibrium means. There is no energy transfer after equilibrium has been established. No net energy transfer. Now if you look at these quantities, there is one small modification I can make, and that is in EA. Can I change this EA to EB?
Yes, minus 90.
Right. So my total energy remains constant. So my energy is not increasing or decreasing. The total energy remains constant. ठीक है, जो किसी ने सवाल पूछा था. So energy is EA plus EB. And this means that EA can be written as E minus EB. This means that DSB over DEA can be written by the chain rule as DSB, DEB, DEB over DEA. Now what is DEB over DEA? It is minus 1. This object is minus 1. So I can put this equal to minus DSB over DEB, which means that if I look at this expression, DSA over DEA equals minus DSB over DEB plus, right? This becomes plus. Now when the two objects are in equilibrium, you've already posited, you've already claimed that the temperatures are equal. So this object for this parameter for object A and this parameter for object B are equal. So would they be equal to the temperature? Can we say that this object is equal to the temperature? They must have something to do with the temperature, because in equilibrium the temperatures are the same. So this object is related to the temperature and this object is related to the temperature. Now if you look at this graph, the question I would like to ask is, the slope here is positive. The slope here is negative. But if you look at the DSB versus EB slope, is it positive or negative? That is why I come back to this graph here. Okay. This is EA, this is SA. It's a positive slope here. If I take this to be the EB axis and this to be the SB axis, what is this slope? Is this slope positive or negative? It's positive. So what I'm really doing is that I'm plotting this graph on top of this graph. This is the DSB over DEB graph, because for this graph the axis is EB, like this. Alright, so both of these slopes are positive. This is a positive slope and this is a positive slope when we consider SB versus AB. Now which of these slopes is higher? This slope is higher. But what about the temperature? Is it higher or smaller here? Smaller. So the slope is inversely related to the temperature. And we have this condition: 1 over T equals ds over dE. So by looking at the entropy versus energy graph, you can tell what the temperature is. Here the slope is larger, the temperature is smaller. देखो ये बात ध्यान से सुनो. Here the slope is larger, the temperature is smaller. Slope larger means it can absorb energy and increase its entropy by a large amount, and that is what a low temperature object really wants to do. Here the slope is smaller. The slope is smaller, so even if it loses a large amount of energy, its entropy doesn't decrease much. And that is favorable from the point of view of second law of thermodynamics. You don't want to lose your entropy much. And an object which can lose a large amount of energy and still its entropy does not decrease much must have a higher temperature. It can afford giving away energy. It's a very generous state. It can afford giving away money. So this slope is inversely proportional to the temperature. Smaller the slope, higher will be the temperature. Here, larger the slope, smaller will be the temperature. It will absorb small amounts of energy and would like to increase its entropy. So I think there will be one more lecture to wrap up all of this discussion, and before we break for the class we can have a couple of question answers. Ji. How can you create a from just an इस वाली चीज के अंदर देखो कांस्टेंट बिल्कुल लग सकता है इसके अंदर, लेकिन थर्मोडायनामिक्स बिल्कुल आप ठीक कह रहे हैं कि जस्ट मेकिंग अ क्वालिटेटिव ऑब्जर्वेशन, we are just putting this equal to 1 over temperature. We can put a constant here, but all the units in thermodynamics are adjusted such that this constant is unity, and we can prove this.
Sir, is that the average equilibrium or just
Which one?
The E part?
This one?
Yes, sir.
This is the total internal energy in that particular object. So there are more questions, we can have that after the class. So thank you very much.